the starting point for 3D printing anything is you need to have a model. Now, some 3D prints, you might be able to download the model you need, but for engineering, a lot of things become custom. So you start with a CAD model. And to translate this into a 3D printable item, okay, finish things as a solid. This one happens to be a GoPro mount that I, CAD'd up and created for a drone. In fact, you can see if I expand the other hidden solid body, you can see the simple representation of my little GoPro, and this is just a little cage that I can squeeze and bend and get the GoPro into and then attach with a wraparound Velcro strap to the frame of the quadcopter. So we need to go ahead and hide the GoPro because I don't want to 3D print that. But the way you want to save this in a file usable by 3D printing software is to save it as an STL file. So just go to File, Save As, change the format to STL. Originally a format made for stereolithography, so that's why it got adopted by 3D printing. And under Options, you want to make sure that you're saving in millimeters. So if you get a weird scaling when you import your 3D CAD drawings into slicer programs, you might have accidentally set this to centimeters, millimeters, inches, whatever. You want it set to millimeters for proper scaling. That's what all these slicers assume and print in dimensions of. There's not a lot of extra information in STL files. It's a very simple representation of the 3D object. So binary, millimeters, and then in terms of resolution, this is basically how many triangles the SOLIDWORKS program is going to save your 3D file in. I have set a custom with a fairly small angle and deviation tolerance, and you can just adjust those to your liking if you want things more coarse or more fine in the final representation. Really, the artifacts of 3D printing usually outweigh any sort of 3D structure artifact that remains. So anyway, just save the file, and then that is the input we will need for our slicer program. In fact, it's cool in SOLIDWORKS. It actually shows you the 3D representation here temporarily. Noticing again, as in SOLIDWORKS style, you get a few missing edges and things, but in my experience, they still show up whenever you get into the slicer program. You'll be able to tell otherwise. Triangles, 1,410. Those are basically the surface triangles that define the object. File size, very, very small, 70 kilobytes, binary format. Like, all I have to do is click yes. Sounds good? Okay, it's saved. So that's the first step. The next step to 3D print a custom object is to slice this object. You're going to turn this 3D STL file into a series of layers that the 3D printer can just follow the G-code properly to print out plastic in the right areas, to move the print heads into the proper places. You're going to turn this into the universal CNC machine language called G-code, and 3D printers use a reduced set of G-codes. They don't have the full set available in most of the print firmwares, but it's plenty enough to do 3D printing with. As I open this up in repetier host, which is my preferred slicer, well, it's not even a slicer. It's actually just kind of a controller GUI front end. It's where I learned from, so it's where I'm most comfortable. There are many other things available. There's a Cura slicer, many sort of different GUIs and front ends, but really it just comes down to find one that works, find one that has a feature set you like. For me, repetier host works nicely because I also utilize repetier server, as you'll see for my printer setups here. So we've loaded the file, but you notice this is presently in a cylindrical volume. That cylindrical volume corresponds to my Delta 3D printer, and I don't want to print this on the Delta. We might talk a little bit about Delta style 3D printers, but to keep things simple, I want to use my Cartesian printer. So under printer settings, I want to go up here and change away from default to the A8. Okay, so there we go. So now it is set up to use the A8's print volume, print bed size, and you notice the position needs to be adjusted. So I can click that center button, and that automatically moves and snaps the object to the center. If you have any need to rotate or otherwise, you can sit there and click these 90-degree rotation increment buttons and move the part around. This part was designed specifically to be printed in that orientation. You notice this tab down here at the bottom sits nice and flat and flush with the print bed. To avoid support structures wherever possible, you want to avoid overhangs wherever possible. And while this part does have overhangs, we'll be filling that in with a small amount of support. And yes, it was a bit of a struggle to get some of that support out of the part. Yes, the part finish did suffer for having support underneath these overhangs, but overall it is worth it to save a little bit of weight on the mount, and again to make sure it was flexible enough to put the GoPro in and out. All right, so the next steps, after you have it positioned in the way you like and the printer's configured in the way you want, you just simply go down these tabs. This is where you actually get to the different actual slicing algorithms. Cura slicer, slicer with the clever 3 placed instead of the E, and then Prusa slicer. For me, I've always used Cura. It works just fine. And if you want to mess with configuration, all the settings are underneath that configuration tab. I have a couple other videos. The advanced repetier host video goes into some of those topics. My classic settings I run with is usually 2 or 3 outline passes just to make sure the 3D printing nozzle is good and primed. When the 3D printer starts, it usually doesn't print for the first few centimeters. So if you do a few outlines, not only is it helping confirm that your bed is level across the entire region of the printer to be printed on, it also helps make sure that the plastic is flowing and moving properly through the nozzle by the time you start printing any sort of important first layer material. So slicing is pretty easy. The biggest thing to pay attention to is that you want to make sure you have set your support structure as you wish. No support structure means it will try to print this part exactly as shown, and I would expect that to fail or look terrible because of these large overhangs. FDM 3D printers need to set the plastic down onto something, and bridging is possible to a certain extent, especially if you've spent the time or the money on a very high-end 3D printer or very good 3D printing calibration. So some printers are configured to work well with bridging. Mine does okay, but it's not amazing. So let's just put the support to everywhere. The touching bed is basically only supporting where the part itself is going to be, where the support structure will touch the bed. It won't do like the intermediate holes and passageways as we had here, because this support structure just needs to go from one upper surface of the part to a lower opening of that window. So that's a part-to-part support structure, so it would be excluded if we just said support structure touching bed. So everywhere, go ahead and click slice, and it does it quite quickly. It's turning that 3D model into a series of instructions, pathways for the printer to follow. So you can see it's actually filled in with this automatically generated support structure. Everywhere there's an overhang, everywhere that there was one of those windows, it's been filled in, and we can actually show you single layers, one by one, to let you preview what the printer is going to do. So layer number 1, this will be the first one that gets laid down. You can see the outline that the printer is going to follow. That's the outline that I have set to make sure the nozzle is primed. That also shows you this is where the part's going to be printed. And if those outline beads of plastic don't stick properly to the print bed, then your first layer probably also is going to have some adhesion issues. It's a very quick gut check to figure out if your bed is properly leveled. So okay, first layer, second layer, third. This is really just a convenience thing. You don't have to check this every time. But you can see whenever it gets to areas of the print that are going to be near the outside, it does a solid infill. That helps that skin of the 3D print be strong, but on the inside it's actually got this very sparse, and you can set the percentage of infill on the other portions of the part. So most 3D prints are actually quite hollow on the inside, and they do that to save print time and plastic. A 100% infill part takes a long time to print and really may not be all that much stronger than some of these reduced infill pieces. So here's the first kind of cross-sectional cut showing support structure. You can see these little 90-degree semicircles here in the corner. That's the actual part that's going to be kept. And all of these very sparse, single outlined, automatically generated support structures here are meant to be broken away, loosely attached. Believe it or not, even though these little visual representations of the plastic glob have space between them and the frame, they'll be lightly attached whenever that's printed. So it's ideally you would just push them out with your hand, but usually it takes a little bit of tool use and a little bit of work to get that support structure out. But overall, let's just look at the complete code again. I like this. Orientation is right. It's printing in the upward configuration, so I want to go ahead and save this to file, and you just save it anywhere you care to. I'm going to save it in the same folder I was working before, and it now saves it as a .gcode format. If you directly want to control the print through USB, like perhaps most printers have a USB port on them, so they can receive serial motion control information over USB from a computer. Instead of simply just going to slice, and then saving to a file, you can then go to manual control of the printer once you have connected. If you have a USB connection, you can click connect, and then you'll be able to manually control and eventually just click the print button here through repetier host. This software package is capable of feeding print information, Gcode directions, instructions on extrusion and position and everything else out over USB into the printer to print directly. This makes it much easier to control the printer just through buttons you can click on a screen than usually in most of the printer interfaces that are a little bit low budget in terms of interface. Yes, you can scroll through menu selections. Yes, you can usually press the scroll button, much like a volume knob, to actuate different instructions. It's possible to move the printer that way. It's possible to prime a printer that way, but the interface of a standard desktop or laptop computer is a much simpler way to go about, especially readying a printer, leveling a bed, and on all those other tasks. At this point, there are many different ways you can get your data to the 3D printer. You can either plug the micro SD card into an appropriate reader and copy the file directly to the micro SD, then physically transport the micro SD into the operating board of the 3D printer, most of which have a little SD card, a micro SD reader, and then use the buttons on the 3D printer to navigate through the different submenus and to load the file and press print. That's where I started with 3D printing. That's where most people start, and very quickly it becomes an obstacle. That's kind of the slowest part of getting the prints going. So what you're seeing here on the screen is my preferred method, which is kind of a high-level method of running what's, in my case, called repetier server. There's another server type program called Octoprint, but what I like about repetier server is it lets you use multiple printers controlled by a Raspberry Pi. So I have a Pi 4 sitting over in between my two printers, and each one of them show up here. I have the ANET A8 printer, which is a Cartesian style printer, and then also have the K200 Delta printer, which is a little bit, smaller X and Y build platform size, but it's very tall. But really, I hardly print anything of large scale anyway. But it's really convenient to be able to say, like, oh, on the ANET, I want to go in and go to the printer, and you can see all the different files that are loaded for you to print from. Now, if you pay for their license, it'll give you like a nice visual picture of what that file entails, but for now I'm just using the free version. So what you do here is say I want to upload Gcode, and you select your file wherever it has been saved. So I'm going to upload the GoPro drone mount.gcode. So it's uploading the file, and this is my computer sending it to the Raspberry Pi over Wi-Fi. The Raspberry Pis are plugged into each of the printers via USB, and so that Raspberry Pi will just live to send information to the printers. The thing I like about that method of operation is that it frees my computer up on my main machine to do whatever else I want. I don't have to live in fear that if I'm using SolidWorks and SolidWorks crashes, and it's going to mess up my print, and then that wastes hours and hours of time. It's nice to have a dedicated low-cost computer, because the task of sending serial data, which is really all it's doing to these printers, is very lightweight. I mean, Arduinos do it. The printers themselves can read from the micro SD card and deliver information plenty fast enough for the motion controller to keep up. But I have experienced myself, and I've seen other people experience print failures due to software on a desktop, power interruptions, random freezes, and otherwise it's just a shame to lose hours of print time because of some little glitch in either USB communication or a computer problem. That's why it's nice to have a bespoke, either use the printer hardware itself and go through the hassle of moving SD cards back and forth, or you set up a small print server, Octoprint, repetier server, or something like that on a low-cost Raspberry Pi. It even works on a Pi Zero, which are very, very small, even cheaper Raspberry Pis that can be used as a print server. So anyway, at this point, all we have to do, assuming our printer is set up, properly leveled, and everything else, you just click the print button on the GoPro drone mount G-code, and that will initialize the server to send that information to the printer, and it's off to the races. Whether you are directly plugged into the printer via USB, or if you are using a Raspberry Pi or print server like we're interfacing with here over a web interface. This is just Chrome interfacing with a remote web server. There will be a method that you can move the printer, turn on and off the heated bed, the extruders, set temperatures. You can control, home, and otherwise affect the printer remotely. Right now we need to replace the filament in this printer. It recently broke, and if you're walking up to a printer for the first time, that probably isn't loaded with filament. So to do that, you first have to heat up the extruder. You have to turn it on, which it's been a little while for this one. Instead of off, I want it set to the PLA temperature of 195 degrees Celsius. And you see, okay, it's just switched it on. I can reference the screen on my printer, and yes, it's ticking up to 30 degrees C, 32 degrees C. It's heating up, and it has set 195 degrees C as the target. This is important so that the printable plastic inside of that nozzle becomes liquefied and you can actually pull it out. Okay, now that the printer has reached 195-ish degrees C, I mean exactly there, plus or minus 2 or 3 degrees Celsius isn't going to hurt. I want to go ahead and use the stepper motor driven extruder to retract this old filament, this old broken filament out of the printer so I can put the new filament fed by the spool into it. So in this case, let's retract 10 millimeters at a time. This can also be done sometimes, like on mine, it has the ability to press down this filament tensioner, and that releases pressure, and if the extruder is warm enough, it should come loose, but I appear to have just broken it off, which is less than ideal. The next step, we'll see if we can feed this through, although I have my doubts, is to cut at an angle this filament. I'm going to, seeing that this exposed area is very brittle, I'm going to cut off a decent length. And by cutting this at an angle, with some of those flush cutters, you make it pointed and much easier to thread into the proper location. Without doing that, it's much more challenging. This one may prove to be a bit of an obstacle anyway. Finally, okay. So you see, all of a sudden, I got the plastic fed into the proper location, was able to push the previous plastic out, and maybe don't go initially and grab this, but it cools off very quickly. You can see it's already solidified down below its glass transition temperature. So you can just take out the previous filament, and now I also realize that I've threaded this through a really dumb part of my printer, and I have to fix it anyway again. Whoops. So anyway, press that threaded relief, and you can see actually it's put a point on this because that's where it's fed into the nozzle. I made a very pointed filament end. So I'm going to go ahead and put another slanted cut on the filament to make it easier to feed. I'm going to unthread this from that hole in the printer. I don't want to feed it through there. I was just holding it there earlier and mistakenly left it. Relieve the cog tension, feed it in, and find the proper pathway just by feel. And pushing some out by hand is no big deal. It gets it properly primed, and you're set. I usually let that dangling plastic cool for a second, grab it with my hand, and we're pretty much ready to go. So at this point, the machine has proper plastic fed into it. If you need to do a filament change, maybe from PLA to ABS, PETG, or whatever else you might be printing with, totally a great time to do it. These type of flush cutters, or any similar style of cutter, are invaluable for 3D printing, so definitely get yourself a pair. So at this point, we just go back to the print menu, unless you want to move things around. I should demonstrate that. At this point, you can move the printer if you want. Move it left and right. You can move the print bed itself. You can see that's just sending signals to the stepper motors. It's sending Gcode commands across Wi-Fi through the web-based interface to the Raspberry Pi. The Raspberry Pi interprets that as it's running the software, sends it out through serial to the printer. The printer then says, oh, I just got a command that says move the x-axis 10 millimeters. It translates that to a number of steps. It needs to move the stepper motor, and then off the bed goes. Really, to us, click the button, things happen. The z-axis in this printer is actually fairly slow, and you'll probably find that common to many 3D printers because they only go up a small amount of distance at a time. So really at this point, you can go down, click print on our GoPro drone mount.stl, and you'll see the printer go to its writing location. It goes through the homing operation. That's what just happened there. The printer went to its limit, smashed up against that limit switch. In the x-axis, another limit switch is beneath the bed in the y, and now it's descending in the z until it clicks that limit switch hidden there in the z-axis. You might say, that seemed dangerous putting your hands that close to this, and it Okay, you do need to watch for pinch points. You need to be safe. But one nice thing about 3D printers is that these motors in the end are so weak because they're driving a very light load that it's very easy to overpower them. Uh, if something got stuck, you're more likely to ruin your print than to ruin your hand or your arm. Don't go putting clothing into weird places. Still use all proper safety techniques, but it should work out okay. So right now the machine is waiting to hit its ideal temperature, 210 degrees C, and it's off to the races. This bed has already been pre-leveled. In fact, if anything, with such a light trace for the first layer, I might have my bed a little bit too close to the nozzle. But you see now it's printing that outline we spoke about, and you see the print nozzle itself got rid of a glob at first, and it's improving the flow of the nozzle as it goes around. So this priming step really does help you lay down a good first layer. And for those of you more seasoned with 3D printing, you might know that the first layer is kind of everything in getting a good 3D print. As long as you have a reliable machine with a reliable code, if the first layer goes down well, it will remain properly adhered, and you should have success with everything else going as planned. This is an example of a Raspberry Pi Zero. You can see it's appreciably smaller than the Raspberry Pi 4 print server that's running right now. This is actually what that web interface and all of the other work is running off of. I don't want to maybe disturb it too much for the sake of running this print. If anything ever goes wrong, of course, the emergency thing to do is just unplug the printer. It should probably be okay if that happens. There is an emergency stop button through the web interface. You can cancel prints through the web interface. It'd be hard pressed to find a real emergency with 3D printing. Already at this point, if the print did not go well, I'd have so much plastic down on the masking tape that it'd probably be best to just go ahead and replace that masking tape region. I print on tape. You'll find lots of other recommendations. There are some really nice build surfaces. Some are magnetically mounted, some of them clamped down. There's some really great stuff out there available. But for me, tape is cheap. It's kind of it's a safety feature because if I just get it really stuck to the tape, then at least I can peel the tape up off the bed and I don't risk, fusing something to the aluminum print bed of my printer. And overall, I've used it for several years and it works quite nicely. I just so happen to have a completed print of what you're seeing there, and I'll go ahead and set it. Well, maybe I shouldn't set it. Set it right there so you can see what is eventually going to be printed out. It'll push it out of the way if it needs to. But it'll go layer by layer, up and up, and it will eventually print those support surfaces, support structures inside these voids that we talked about earlier. And I just peel those out mechanically with some pliers, a multi-tool, and other devices. Just clip them right out. So at this point, it's just a matter of watching the printer to make sure it doesn't catch on fire. That can happen. There's a decent amount of current being put into the heated bed, so a decent amount of current being put into the heated element of the printer. And whenever you're dealing with electrical heaters, especially resistive heaters like those, there is a risk if they get into a thermal runaway type circumstance that they could catch fire. There's also been some fires started by quality control issues with these boards. They're mass produced at very low cost. So observing these printers while in action, at least being in the same room so you could stop a small fire or unplug something if an electrical fire started is ideal. If the printers are in a non-flammable enclosure, then it becomes more acceptable to be distant from them. So that way, even if the printer does catch fire, it's prevented from spreading to the building surrounding you. That would make it more acceptable for standalone print use. On the subject of bed leveling, this is important for getting a high quality print. You need to make sure that as the print head moves across the bed, it doesn't matter if the printer is level on earth, it doesn't matter if your table is level relative to the printer. The only thing that matters is as this printer head traverses left and right across the bed, forward and back, that the bed is equidistant from that nozzle in as wide of a range as you can get, to as accurate of an extent as you can get. The best way to do this is the same way we check for tool height on a CNC machine. So first of all, make sure your extruder's off. You don't want to start burning any pieces of paper. Mine was actually quite warm right now. It's still up at 210 C, so I'll have to wait a little bit for it to cool down. What I typically like to do is take the extruder to each corner. That also happens to be where this bed has adjustable screws beneath the bed. And I place a piece of paper down on the bed, and this, you're going to lower the print nozzle down on that paper to the point where it pinches. So using my left hand, I'll move it. With my right hand, I'm Using my left hand, I'll move it. Using my right hand, I'm adjusting the print controls on the computer, setting things at first to a 1 millimeter Z increment, because I expect to be approximately 1 centimeter above the bed right now. Looking down from the side to see how close the print head is to the paper. Okay, we're really close now, so I'm going to change this down to 1/10 of a millimeter in Z for each input I give. Moving the paper. Still not pinched. Don't feel any drag yet. There it is. There's the little bit of drag from the print nozzle head touching, and this occurs at a Z height right now. It says of 0.2 millimeters. So what I want to do is adjust the screws, are usually the easiest path. Adjust the screws so that the print bed will just barely touch the paper at a Z height of 0. So in this case, I would simply take a screwdriver, puncture through the top of this plastic to hold that screw in place as I either tighten or loosen the thumb screw underneath. I'm not going to adjust this printer's level right now because it's fairly tuned in and has been successful across the entire bed. But if you repeat that process with the assumption that the bed is, the aluminum that makes up the bed is reasonably planar, then really you might only have to do this at perhaps 3, but usually I do the 4 corner points to get the best level that I can across the entire print bed. So you simply just move it across to check the other corner. Whoops, a bit far, but that's okay. And then you would again repeat that Z leveling process to adjust the screw until what reads out as 0 Z height on your screen is actually the point at which the nozzle starts making contact and dragging on the paper. You want there to be a little bit of height between the Z0 and the 0 of the bed, so that way whenever the nozzle prints the first layer, it basically presses the plastic down, it smushes the plastic a little bit onto the surface to get good adhesion. You don't want to be 3 hours into a print and then just your print comes loose on the print bed and skitters across, because that ruins the entire thing. You fail the print in that case. So check that on all 4 corners. Check the Z height. Adjusting usually mechanically is easier than adjusting electronically. The level of the bed. If you're having problems with first layer adhesion, it's usually due to some sort of bed leveling issue. So adjusting that properly is one of the first keys to having a successful 3D print.